So today I'd like to do a problem with a bit more complex geometry. So this problem, 1636, reads, at the instant shown, the shaft and the plate rotate with an angular velocity of omega equals 14 radians per second, and an angular acceleration of alpha is equal to 7 radians per second squared. It asks you to determine the velocity and acceleration of point D, located on the corner of the plate at this instant, and then it asks you to express the result in Cartesian vector form. So we're given information about rod A and how it rotates, and we have to find the information of how point D on this plate, which is attached and part of the same rigid body as rod A.
Okay, so let's get started. So I've just drawn out the exact same diagram that was in the question, and I wrote down a couple things we know. Firstly, that omega is equal to 14 radians per second. Secondly, alpha is equal to 7 radians per second squared. And then just a couple helpful equations that will help us to solve the problem. So first off, we know information about this point A. We know that this rod is rotating at omega equals 14 and alpha equals 7. So we want to define point A, the thing that we know about, and then we want to try and first we want to define the stuff that we know, and then we want to define the stuff that we don't know in terms of stuff that we know, and then eventually we will know the things we don't know. So let's start by finding the position of A relative to the origin right here. So we can see right away that the x-axis is here, and A is all the way back here. So A is located at negative 0.3 I hat. And if we look at the y-axis, which is coming out here, A is positive, and it is 0.2 j hat. And finally, if we look at the z-axis, we see that A is also positive in z, and it's 0.6 k hat. So this is our RA, and this is with respect to the origin. But we know omega and alpha in terms of A, and we want to translate that information to the origin. So we're going to turn omega and alpha into vectors by multiplying them by a unit vector. So first we have to get our unit vector. So our unit vector is just our distance, RA naught, divided by its magnitude. So our unit vector is RA naught divided by magnitude of RA naught, and that gives us negative 0.3 I hat plus 0.2 j hat plus 0.6 k hat, all divided by this lovely long square root term. So when I calculate that out, I find that our unit vector is equal to negative 3 over 7 I hat plus 2 over 7 j hat plus 6 over 7 k hat. Okay, so now we know our unit vector, and we can find our angular acceleration and angular velocity, and they'll be vectors now instead of magnitudes. So omega is equal to omega times this unit vector. Oops. And when we multiply our 14 by this long vector here, we will find that it's equal to negative 6 I hat plus 4 j hat plus 12 k hat. And likewise, when we do the same thing for alpha, we find that our vector alpha is equal to negative 3 I hat plus 2 j hat plus 6 k hat. Okay, so now we know what these actually are in terms of the body, but the whole question is asking us about the movement of point D. It wants the acceleration and the velocity at point D. So it probably goes without saying, but we're going to need to find the vector from the origin to D. So we can find that just by looking at it. D's way the heck back here, the origin's here. So if you look at the x-axis, we know that D from the origin is in the positive direction. So it's 0.3 I hat. And it's located negative in the y direction. So it's negative 0.4 j hat. And it's located at the same level as the origin in the z direction. So it's plus 0 k hat. So you don't even have to write that term, but I did just to be thorough. Now, we know that, and it's time basically to start using our equations. So we know that if velocity of a point on a body is equal to the angular velocity of the body crossed with the vector from the body, the vector to the point on the body. So in our case, VD is equal to omega cross RD. And we already know omega and we already know RD, so we can just build a nice little matrix and solve for this pretty simply. So IJK omega is negative 6, 4, and 12, and our RD is right there. It's 0.3, negative 0.4, and of course 0. So when we actually work out this cross product, it turns out that this answer to this is 4.8 I hat plus 3.6 j hat plus 12 k hat. And this is our velocity d, and it is measured in meters per second. So we want to do the same thing and find the acceleration at point D. So we're going to use this equation here, and I'm running out of room, so I'm going to probably just overlap this so you can still see the equations in the problem. So now, for the acceleration at D, we have alpha cross RD minus omega squared RD. And that gives us that's a negative sign. That gives us our acceleration at point D. So I want to break this up into steps just so it's like pretty clear what's going on. So first I'm just going to do alpha cross RD. We found alpha and RD already. So alpha was negative 3 I hat, 2 j hat, and 6 k hat. And RD was negative 0.3 I hat, 0.4 j hat, and 0 k hat. So when we work out this cross product and add it all up, it's negative 2.4 I hat minus 1.8 j hat minus 0.6 k hat. So now we have like the gross term here, and we want to find out what omega squared RD is. Well, omega squared RD can be just written as omega cross RD. So let's do omega cross RD first, because that's, well, order of operations, and it's also easier. Okay. So omega cross RD gives us, so omega was negative 6 for and 12 k hat, and RD was 0.3, negative 0.3, and positive 0.4. Okay. So when we work out this cross product, you will end up with 4.8 I hat plus 3.6 j hat plus 1.2 k hat. And so now we can do this long term as another cross product. So I might run out of room here, but let's see if we can fit this all. Okay, so I'm actually going to slide this up just as a precaution. And okay, so we're doing this. So I, j, k, and we just got 4.8, 3.6, and 1.2. So when we carry out this cross product, we'll find that this term is equal to negative 38.4 I hat plus 64.8 j hat minus 40.8 k hat. Okay, so now we have all our terms, and all we're doing is some vector addition. So acceleration of d is equal to alpha cross rd minus omega squared rd. Well, our alpha cross rd is up there, 1.8. And we're minusing our omega squared rd term here. So I hat k hat there. And then so when we work that all out, it gets us a nice number of acceleration of d is equal to 36 I hat, oh, that's a j, other I hat minus 66.6 j hat and 40.2 k hat. And there you have it.